Okay, I'm going to do one more video about acid base. I realize there's a few topics that I did not cover, so I'm going to do those here before I move on to redox. Okay. Now, I mentioned in the last video about strong acids and weak acids, and I think it ended when I was talking about a weak acid, and I used carbonic acid as an example of that. I want to cover a weak base now, just to finish that that subject up. And the one I'm going to use is ammonia, I think. So, let's see this thing. Yeah. So ammonia is NH3. It exists as a gas. Very important chemical in our economy. And I'll draw what it looks like too. Well, it just looks like what you kind of expect. It looks like this, shaped like a pyramid. NH3. Okay. It actually is a weak base, and I'll show you why in a second. When you take NH3 gas and you mix it with water, the ammonia dissolves in water, similar to the way carbon dioxide dissolves in water. It dissolves in the water, and it partially forms, NH3 in aqueous. But the NH3 will also mix with some water. So let's show what that looks like. Draw my ammonia. And when water comes around, HOH, it turns out the affinity here, from electricity standpoint, electromagnetism standpoint, is that the nitrogen has a little bit of an excess negative affinity, and so it can actually take on and grab a proton away from some of the water molecules. So what happens in solution is you actually end up with NH4, which is net a plus, it's net plus, and hydroxide, which of course is minus. So some of the ammonia in solution will dissociate, forming, and now I should actually write it up here, partially forming NH4 plus, which is called ammonium, and hydroxide as a minus. Now, it doesn't fully dissociate, and that's why it's a weak base. It partially dissociates, and again, a lot of it stays in solution as just NH3. But it partially dissociates like this, producing a little bit of this base, this hydroxide base. So, when you, for example, mix ammonia in a solution like I've drawn, and then you take this and add on HCl. Now in solution you've got ammonium a little bit, hydroxide a little bit. Now you're adding in something like an H and a Cl, and you can guess what happens. These guys immediately join up. Essentially the ammonia neutralizes some of the HCl, neutralizes some of its acid, and what you're left with is essentially ammonium and chloride. And ammonium chloride, in fact, I think it's even in your lab kit. It's just an ordinary salt that dissolves freely in water. Okay, so in this case, it kind of shows how ammonia, when dissolved in water, partially dissociates, becomes a weak base. That weak base then can be involved in an acid-base reaction by neutralizing other acids, resulting in a salt. Now, that was the other thing I wanted to kind of point out when I was talking about acid-base neutralizations, is that this is actually kind of one of the ways of thinking about acid-base reactions in general. Is basically an acid typically reacts with a base to form water and some salt, and that's kind of a really kind of a high-level way of describing what an acid-base reaction is. The base neutralizes the acid to form water, and also results in the stuff left over is a salt. The classic example of NaOH and HCl we did in in the previous video, sodium hydroxide and hydrochloric acid. That neutralization results in water plus the salt would be sodium and chloride, sodium chloride, table salt. And in the case that I've drawn in neutralizing or having ammonia neutralize HCl, the salt is ammonium chloride. But it's still salt. Okay, that was one thing I wanted to cover. The second I want to cover is I wanted to introduce one more weak acid real quick because I'm going to use it in the next video, and it'll come up a lot. And it's basically some of the weak acids are actually organic acids, and I'll only show you why it's weak. So the one I'm going to show you is the active component in vinegar. It's called acetic acid. And acetic acid kind of looks a little like ethanol. If you remember how ethanol looked, ethanol had this sort of shape already. But in ethanol's case, we had an H here, an H here, and an OH here. That was ethanol. Acetic acid is similar in shape, but this C, instead of having the H's, has a double bond to an oxygen, and then a single bond to another oxygen, which has an H. Okay. Now, this is acetic acid. Reason why it's acidic is that this last little H is kind of a candidate to get kicked out. Basically what happens is that these electrons just kind of roll up into this oxygen, making this thing negatively charged, and you end up with also now a free proton. And that free proton can attach to another water molecule to form hydronium, for example, or whatever. But this is a partial dissociation at this point, meaning most of your vinegar is going to be made up of acetic acid molecules, meaning the H is still attached to the O. But some of them will dissociate in the same way that I kind of showed with ammonia. Some of them will dissociate to form a little bit of acid, and that's why this is called a weak acid. One thing I want to show you that's interesting about this too is that you see how I drew this? I drew this as this oxygen is charged and this one is not. In reality, what happens is that some of the time this is the one that's charged and this is the one that's not, and the other part of the time it's just the reverse. And what happens is just by electrons kind of bouncing around between this covalent bond and this covalent bond, it actually produces a more stable form, which is some of the time this is negative, some of the times this is negative. It's almost like you can consider this oxygen having a half negative and this oxygen having a half negative. This results in a more stable ion actually than if only one of these elements had to take the whole charge on by itself. This is a very, very, very important concept in organic, and it's going to come up over and over again in organic. But we're going to introduce it in a number of other places too, even in this course, because it boils down to the fact that the ability for these oxygens to share the charge lowers the energy level of this ion. And a lower energy is essentially a more stable ion. This is a theme that's going to come up a lot, again, especially in organic. Okay, so I kind of want to mention that. The other thing I wanted to mention, along the same theme that I just mentioned here, where the charges are sort of shared, actually comes up in pure water as well. And I want to draw it. I know you're going to think, you may say, I don't see why that's so important, but bear with me. So when we talk about hydronium, okay, I had drawn hydronium in the first video, which is essentially another way of looking at what a free proton looks like. And again, a free proton isn't really free. It immediately attaches itself to water and becomes something that looks like this. And what I said is that in this case, this is positive and here's our neutral water and this is hydronium. But of course, another way of looking at this is saying, well, the whole thing is positive, but it's not this H that's positive. It's really kind of This H about a third of the time is positive. This H is about a third of the time the positive, and this one a third of the time positive. Essentially, with all three able to kind of share the charge, it makes this ion more stable. Certainly way more stable than something like a free proton, a free hydrogen cation, because then this ion has to take the full charge all the time. Okay, so hydronium itself is an example of one of these shared energy states that makes the ion more stable. To go even further, though, is that this isn't even necessarily how it works in pure water, where you have pure hydronium rolling around. What happens in the case of hydronium is that this H actually becomes a little more a little more affinity to another water molecule, because, and for that matter, this one might have the exact same sort of affinity to another water molecule, and then the same thing for this top guy. And so at any point in time, for example, this charged hydrogen, imagine it was this guy's turn to be the charge. That doesn't really work that way in terms of terms, you think of it that way. When it's this guy's turn to be charged, there's no reason why it can't say, to heck with it, I'm actually going to go over here. And now you've got nothing but water, 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 and now your hydronium is over here. So at this point then, you can see that the charge across these 4 water molecules and the 1 extra proton, this whole thing has a plus charge. So if you can now you kind of picture this in solution, you've got a little bit of acid, little of a free proton. That proton is surrounded by waters, and it's surrounded in a way to kind of spread out the charge across a number of different water molecules. That in turn makes it more stable. And this is kind of why water is such an effective solvent anyway, is that it has this ability to kind of share charges amongst other charged objects. Okay, that's all I want to say about that one. I do have one more. I wonder if I can get it in. Nope, I'm going to do one more video. So I'll pause this and I'll have one last acid-base video.